Right. We're going to do 2002 structured essay 4 electricity question. So the question says a resistor S, a milliammeter A, and a battery E are connected in series across the points X and Y as shown in figure 1. The milliammeter has an internal resistance of 25 ohms and it requires a current of 1 milliampere for full scale deflection. The dial of the milliammeter is shown in figure 2. The battery has an EMF of 10 volts and a negligible internal resistance. R is any resistor connected externally across points X and Y. Let I be the current through the milliammeter. Right, they have given us the dial of the milliammeter. And first they're asking, when R is 0, the milliammeter reads a full scale deflection 1 milliampere. So they have also given 1 milliampere full scale deflection. Find the value of resistance S. Find the value of resistance S. Right. So what they say is when R is 0, right? So the value of R is 0. The current here is 1 milliampere. 1 milliampere. And the battery has an EMF of 10 volts and there's no internal resistance. Right. So you can see that a voltage of 10 volts is given for both of these devices because here you have 0. Right. So potential gets divided, right? So you can find the potential difference here when it's 1 milliampere, right? They've also given internal resistance of this as 25 ohms. So this is going to be 25 millivolts. It's going to be 25 millivolts. So if that is 25 millivolts, the rest of the 10 volts must be here. Means 25 millivolts, you can also convert this 0.025 volts. That's 0.025 volts. So 10 minus 0.025 volts is the potential difference of S. 10 minus 0.025, that is 9.975 volts. 9.975 volts. So you can apply V equals IR to this. I will do it here. V equals IR. So 9.975 equals 1 milliampere, that's 1 into 10 to the power minus 3 into R. So for R you get 9,975 ohms. So you can also do the working here itself in the space that they have given, right? You can use that space. If you want to do a calculation, you can use that space because they have also given marks for writing what it is. So how do we write this in a proper way? Let's see how do we write this in a proper way, right? So we can say that value of S is equal to, or you can just apply Kirchhoff's and show that right? Simple version of this is applying Kirchhoff's. So you can say E is equal to 1 into 10 to the power minus 3 into 25 plus 1 into 10 to the power minus 3 into the resistance of S. So I'll write that as S. So for this you'll be getting 1 mark. Then we'll get 2 marks for this. And finally simplifying and getting the value of S is 9,975. You'll be getting another 1 mark. So altogether they are going to give 2 marks for this, right? So when you have space, you have to utilize that space that you have. Right. Part 2. Practically, how do you achieve R equals 0? So they're asking, how do we achieve that this R is 0? So in order to achieve that, what you can do is that you can just short circuit these 2 points, or connect X and Y, or short circuit X and Y. So you can write the answer: short circuiting X and Y. Short circuit means you just connect them. So for that you get another 1 mark. One mark for this. Write above value of R in the box corresponding to the pointer position of the deflection of the milliammeter in figure 2. So they have given 4 boxes, and they say it's 1 milliampere deflection, it's a full scale deflection. So they want us to write the value of R. Write the value of R. So we were making R 0. So you have to write that in the box 0 ohms. 0 ohms in the box. You have to write that in the box, but I'm writing it outside now because there's no space. Right. Part B1. When R equals to infinity, what is the current I through the milliammeter? When R is infinite. So when you make this infinite, asking the value of current, right? So I'm going to erase this stuff now. It's a different question. Okay, so when this is infinite, the current is going to be 0 because there's no current through an infinite resistor as you know it, right? So we can write that down as zero. So writing down 0, you'll be getting 1 mark. Practically, how do you achieve R equals infinite? So how do you achieve practically that R is now equal to infinity? You just have to disconnect X and Y. When you disconnect X and Y, the resistance is infinite, that there's no current there, right? So you can say we are going to disconnect X and Y. Disconnecting X and Y, or you can also say open circuit, keeping it without connecting. So for that you get another 1 mark. Part C. what resistances of R give the following deflections of the multimeter? What resistances of R will give the following deflections of the multimeter? Right. So here the infinity also we can mark on the box. When the deflection is 0, that is infinite, right? It's infinite. So here in this box you can write infinite. Okay. We'll come to part C now. Half the full scale deflection. Half the full scale deflection. So let's see. Half the full scale deflection is 0.5 milliamperes. So when there is a current of 0.5 milliamperes in this, so let's see, 0.5 milliamperes. So when there's a current of 0.5 milliamperes, we need to find the value of R, because already we know this is 9,975 change is found, right? So the value of R. So how do we find that? We have to do a small simplification for that as well, right? So let's write the simplification part. Here they have given 2 lines for that. You can say that E, or 10 volts, is equal to half the deflection is 0.5 milliamperes, so that is 0.5 into 10 to the power minus 3 into R plus the other resistance is from the milliammeter and S, so that is going to be 10,000. I think you understand this, because when you add this to this, you get 10,000, right? So then you have to simplify. So you get the value of R. The value of R that you should be getting is 1000 volts. 1000 ohms. It's 1000 ohms. So for getting this answer properly, you'll get 1 mark. Right, then they ask for quarter scale deflection. Quarter scale. Let's see, a quarter of a scale. So the full scale deflection is 1 milliampere. So the quarter scale is 0.25 milliamperes. So we can write there 0.25 milliamperes. 0.25. So you can also apply same equation again. Then equals 0.25 into 10 to the power minus 3 into R plus 1000. So for simplifying, that is, you get 30,000. 30,000. Here previously I have done a small mistake. This is not 1000, it's 10,000. And here the value is not 1000, it's 10,000. So the two resistance values are 10,000 and 30,000. This is what you should get once you simplify. 10,000 and 30,000. So you can mark those values. They say write the above values of R also in the corresponding boxes in figure 2. Right, so we'll go to that point and we'll mark them. So here you should mark for quarter, it's 30,000 ohms. And here for the half you should mark 10,000 ohms. So this is how you calibrate this device, and already you know what it is, right? Okay, we'll say part D says if the section of the circuit with the milliammeter shown in the figure 1 is calibrated Also, for values marked in the dial of the multimeter, the setup can be used to measure an unknown resistance. The unknown resistance is connected across X and Y, and the value of the resistance can be read from the calibrated scale. Propose a suitable standard name for this setup, and you know this name, which is the ohm meter. We call this an ohm meter. This is an ohm meter, right? So writing the proper answer here as an ohm meter, you get 1 mark. Is the multimeter scale linear or non-linear? So milliammeter. Is the milliammeter scale linear or non-linear? That's linear. We can see that, right? And you know, in a galvanometer, usually the scale must be linear, and also you can see by looking at this scale, it's a linear scale. It's a linear scale, right? So there's no doubt in that. It's a linear scale. So we can say it's linear. Is the scale calibrated to measure resistance linear or non-linear? Right. So you can see here we have values from 0 to infinity in this small range. So can you have, think about it, can you have everything calibrated linearly in a small scale from 0 to infinity? No, it's not possible, right? So from the theory also you have learned this. So you know already that it is not linear. So we have right non-linear. That is non-linear. So writing the both answers properly, you get 1 mark. For both answers, you get 1 mark. Fine. Then they say, draw a rough sketch to show the variation of R with I. There's a hint given. You may look at the values marked in the boxes in figure 2. So by looking at the values, they want us to draw the graph of I against R. I against R. So here what we can do is we can look at this. Also what we can do is we can get an equation as well. So I prefer to get an equation rather looking at this. Right? So I prefer to get an equation for this I. Right? So let's see how to get an equation. So when you apply Kirchhoff's, you can see 10 is equal to I times R plus 9,975 plus 25, that is 10,000. So this is a simple equation, right? This is a simple equation. So you can use this. You can use this equation. Let's take it down. So using this equation, we can judge what will be the graph, right? So let's try to make it a graph equation here. So 10 over I is equal to R plus 10,000. So we can say R is equal to 10 over I minus 10,000. So let's substitute values to get a perfect graph here. So what will happen if you make I 0? If I is 0, this is going to be infinite. So infinite minus 10,000 is also infinite. Right? So when I is 0, R goes to infinity. So there is no contact here. And when I increases, R will decrease. Right? And when R is 0, so if you make this R 0, there is a value for I. When R is 0, there is a value for I. It's a very small value. Right? A point. So your graph must be something like this. It comes to a certain value. It should touch the x-axis, but it is not going to touch the y-axis. Right? So this is the shape of the graph that you must get for this. Right? So if you have drawn the graph properly, you'll be getting another 1 mark for this. So this is how you do the fourth structuralist equation in 2002 paper.